Good afternoon, everyone. Welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today we have with us Dr. Glenn Ulrich, presenting on application of methane biofilters for reducing greenhouse gas emissions. We'll go through a few housekeeping items first. We'll be keeping all phone lines muted until the end of the webinar for Q&A. If you have any questions during the presentation, you're welcome to enter them into the chat feature and we'll address them at the end, or you can hold your question and ask it live during the Q&A session. This webinar has been approved for one professional development hour credit. Glenn, if you could go back one slide real quick. Thank you. This webinar has been approved for one professional development hour credit, or PDH. If you'd like to receive that credit hour, there's a attendance form that will be posted in the chat function. It's a web link, so you should be able to access that. If you can't for any reason, please send us an email or a message and we'll get that to you after the webinar. There will be 3 multiple choice questions that you'll have to answer in order to get attendance. We'll also post those in the chat in case you have any issues getting into the form during the webinar itself. And finally, this webinar is being recorded and will be available on the Parsons YouTube channel in the next few days in case you miss any of the content or in the questions for the attendance form. So a brief agenda for today's presentation. We'll introduce our guest speaker, Glenn Ulrich, up front, followed by a core value moment before we get into the technical presentation itself, and then we'll wrap up at the end with a question and answer session. So a little bit about our speaker today, Dr. Glenn Ulrich. He has a Bachelor of Science in Microbiology and a PhD in Microbial Ecology with over 25 years of experience. He's a technical director with Parsons, specializing in developing and applying sustainable biotechnologies for oil and gas, as well as environmental remediation industries. And he's previously served as a lead scientist for an oil and gas exploration and production company. And with that, I will hand it off to Glenn for the core value moment.
Thanks, everybody, for joining me. And thank you, Jessica, for that kind introduction. For the sustainability moment, or the core value moment, I've chosen sustainability because the presentation is focused on limiting greenhouse gas emissions, in particular methane, to the atmosphere. So quick summary of the agenda. We'll discuss the fact that methane is actually quite easily biodegraded. We'll go through some environments where methane is effectively biodegraded, and Mother Nature has proven to us that biofiltration of methane is actually quite effective. But then we'll get into the bad news, and that is cases where anthropogenic activities have created localized pathways and sources of methane that do indeed make its way into the atmosphere. And that's an issue because greenhouse gas, or methane, is a very potent greenhouse gas with a greenhouse gas potential of between 30 to 80 times greater than that of CO2. Then we'll move into a solution for the issue, and that is the application of methane biofilters to intercept these point sources of methane making their way into the environment. And that includes a quick summary of the work that we've done in our laboratory to help develop the technology. And then we'll go through briefly summarize 2 applications of methane biofilters, including at a landfill in South Bend, Indiana, and then also for a leaking well in just north of Edmonton in Alberta. And then we'll conclude. I think the most important slide of my presentation is this one, the acknowledgments. I greatly appreciate all of the work that the Parsons team has provided to make this work and presentation possible, including folks in our laboratory in Syracuse, New York, individuals from our offices in the Midwest who helped apply the methane biofilter in South Bend, and to those in Alberta for their work with an oil and gas client. I especially wanted to thank the city of South Bend, Indiana, and the Indiana Department of Environmental Protection for their support of this work. And then also wanted to especially thank the major oil and gas company in Alberta, Canada, that has supported our work in understanding methane emissions at oil and gas wells there in Alberta, Canada. And then finally, but not least, thank you to Dr. Aaron Cahill with Harriet University for his ongoing technical support of our work in Alberta. So we'll begin with the good news, and that is the fact that methane is easily biodegraded in environments where methane is effectively biodegraded. This is near and dear to me. This was a lot of my graduate school work was focused on the biogeochemistry of methanogenesis, and ended up working in the oil and gas industry on the process of methanogenesis. And lo and behold, now we're working on degrading that methane. So we'll start with a picture in the upper left. This is a methane seep in the deep sea. These sources of methane include methane hydrates that can be released. Also includes, there's essentially could be pathways to deeper sources of methane, supplying ongoing methane releases to these seeps. That methane can be effectively biodegraded as the methane migrates through these thick and deep water columns, both under aerobic and anaerobic conditions. Upper right shows an example of how methane can be degraded anaerobically. Prior to approximately 25 to 30 years ago, it was believed that methane degraded only under aerobic conditions. And it was a significant discovery in that we were able to show, not me personally, but folks working in the area of anaerobic biodegradation were able to show that methane can be degraded with sulfate as an electron acceptor. So here we have organic rich sediments that is supporting methanogenesis and the production of methane in these sediments. That methane migrates upward and it meets downward migrating sulfate that is sourced from seawater. Where those two meet, shaded in the light color here, we have anaerobic methane oxidation. Again, the importance of this discovery is that methane can be indeed degraded anaerobically, and likely is an important process in mitigating greenhouse gas emissions. The other thing I wanted to point out with this slide is that in some cases, the CO2 generated from methane degradation can precipitate and form carbonate minerals. The case on the lower left shows an example of, I suspect, where many people are somewhat familiar with the process, where we have a petroleum release to the environment. That petroleum, in this case, migrated vertically into the shallow subsurface. And essentially, in all cases, at least that I've been associated with, at least a portion of that petroleum is biodegraded through methanogenesis, again, resulting in the upward migration of methane. And where that methane migrates through the soils, and we have the vertical downward transport and diffusion of oxygen from the atmosphere, we can have effective aerobic biodegradation of methane. And then the final case, which I think is really exciting and interesting, is the lower right-hand example, where there are specific methanotrophs found in soil that can degrade very low concentrations of methane in the atmosphere. So this is just a few of the cases where in environments where methane is degraded, and the message is it's easily biodegraded, and it can be biodegraded both under aerobic and anaerobic conditions. So that's the good news. The bad news is that through man's activities, we have created pathways and sources for methane to reach the atmosphere. And that includes, in the bottom left, landfills, where we have refuse that's degrading through methanogenic conditions. That methane is accumulating under the caps of these landfills. That methane has to be vented or recovered to maintain the integrity of the caps. In general, the concentration of methane drops to the point that it cannot be burned for use or be flared. And then the methane is simply vented to the atmosphere. Another example of methane releases and pathways includes mines, especially mines that are used for recovering coal, in particular in the Appalachian states. This is a major source, significant source of methane. And then we'll move up to the upper right. In the oil and gas industry, we have hundreds of thousands of abandoned oil and gas wells, roughly 20% of which are likely leaking fluids, including methane, potentially brine, and oil. And then we have gas transmission, collection, and distribution systems where methane is making its way to the environment, including through oil water separators and similar types of equipment. All of which results in an increasing concentration of methane in the atmosphere, and that's shown in the bottom right. The time period there, in case you can't see it, is roughly 1980 to current. And we can see that the current rate of methane concentration increase is increasing currently, or more recently. So that's some of the bad news. And then let's talk about perhaps some ways that we can help mitigate this issue. And that is with methane biofilters. And we'll go through that now. The concept of methane biofilters is not new. This concept has been around for at least 20 years. However, the methane biofilters are slow to make their way into the marketplace. And I'm not sure quite why that is, but it is one of the few technologies that we have available to intercept these essentially millions of spot sources of methane around the world. There's a limited number of technologies that are applicable for that purpose. So the goal then is to demonstrate and develop cost-effective, sustainable methane biofilters with limited or no maintenance. And related to that, we know that these methane sources are long-lived. So we need to develop and apply very low-cost, simple ways to monitor these biofilters, especially remotely, which would prevent individuals from having to visit the sites to see how well these biofilters are performing. And we'll get into a little bit of our work on that area. Ultimately, our goal is to help commercialize this technology. Some of the benefits of the technology, again, methane is easily biodegradable. And that's a welcome news for me, because I've spent a lot of my career working with chemicals that are quite recalcitrant. So really what we're dealing with here is ingenuity in developing effective, sustainable methane biofilters. And I think throughout the presentation, hopefully it becomes apparent that that will require many different designs for site-specific conditions and ongoing development of better, easier, less costly ways to apply these filters. Again, I think I mentioned the benefit for, although methane does degrade to CO2, that CO2 has a 30 to 80 times lower greenhouse gas potential compared to methane. Some people in the atmospheric sciences have suggested that the quickest way to curb global warming is to reduce the emissions of methane, because it does have such a potent greenhouse gas potential. Okay, with that as an introduction of the problem, we'll now go through our work at Parsons to help develop this technology. And it began roughly 5 years ago in our laboratory in Syracuse, New York. And that includes the static bottle tests that are shown in the picture in the upper left. We developed a simple way to monitor methane degradation. And I don't know if this is new or not, but we simply measure the pressure in these incubations. They're spiked with oxygen, not air, but oxygen and methane. And based on the stoichiometry of methane degradation, that results in a net loss of gas, because 2 moles of gas are consumed and 1 is generated. So an example of that work, and some of the results are shown in this figure in the lower left, where we see pressure over time on the y-axis and pressure in days on the x-axis. We see no methane degradation in this case for landfill soils, including the cap material alone. But when we mix that cap material with various treatments, we see significant methane degradation. And a typical result is that we see improved methane degradation rates over time as the methanotropes grow. So that's not surprising. Given that our objective is sustained methane degradation, it's important to control the environmental conditions within these biofilters over time, and that includes managing the moisture levels. We don't want the biofilters to dry out, and likewise, we don't want them to get too wet, both of which would reduce the performance of the biofilter. So we've developed media and methods to control the moisture content. I'll now jump into our first application of a methane biofilter in South Bend, Indiana. It is, again, a landfill. This is an old landfill. It is located in a highly residential area, so there are homes lining the perimeter of the landfill. And the gas, it's important that that gas below the cap be recovered because of those homes. And it's recovered through a series of extraction wells and piping and the gas is then pulled with the blower in the foreground here and vented through the vent, which you can see in the photograph. That vent was initially installed and intended to be a flare. However, the concentration of methane has always been too low to burn. So that leaves us with no alternative other than venting that gas, which has methane in it, to the atmosphere. So again, the goal here is to develop and demonstrate low-cost passive methane biofilter with limited or no maintenance, and importantly, the ability to monitor these biofilters remotely without sending individuals to the site to monitor the biofilter. This is an aerial view of the park in the landfill. Again, we have a series of extraction wells and piping. That methane is pulled to a fenced-in area located here. Hopefully you can see my pointer. The yellow is the location of the biofilter sitting right next to the blower, and the blow up of that is in the upper right. Essentially, we're taking the gas recovered from the landfill via the blower, piping it into the biofilter, and then pulling that gas. Actually, we're not pulling it, it's just migrating through the filter and then pushed through the vent, all via the operation of that existing blower. Some aspects of the design of this particular methane biofilter is we've used local materials to reduce the cost. We have designed the filter to effectively distribute gases within the filter, and that's important because we want to use, most or all of the filtration capacity of that biofilter, which means we have to effectively distribute gases and methane through the filter, and we can control the rate at which we distribute methane into the filter. In terms of sustaining methane degradation, it includes our ability to control the temperature. Specifically, the biofilter is insulated. It does get quite cold in Indiana in the winter. It includes our ability to control the moisture based on the way that the filter has been designed and installed, as well as the media that we use to construct the filter. We also wanted to make sure that oxygen does not become a limiting factor. We included long-term nutritional supplements in the media, and the media is composed of non-degradable media so that it doesn't decompose over time, which would result in loss of structure of the filter media, as well as a secondary utilization of oxygen. So we want to decrease the level of organics in the media to reduce the oxygen demand. And then finally, as I mentioned, the biofilter is monitored remotely, and that includes we have temperature probes and moisture probes at different depths and different locations in the biofilter. Obviously, temperature and moisture are two key conditions for microbial activity. And then we have recently partnered with a company that developed a methane sensor to quantify methane concentrations in the gas leaving that filter. Some pictures showing the media, mixing the media. It's quite important that we get a uniform mixture of media so that we don't have preferential pathways for gas to move through the biofilter. So we've come up with different ways to do that. This is just one of many that can be used to effectively mix the media. And then number two, under the construction photos show, essentially we're building this biofilter from the bottom up. It does include gas distribution piping, both to get gas in and out of the filter. And then, our goal was to leave a biofilter that blended into the natural setting. And so we seeded that filter, and you can see that it's vegetated quite nicely. this is just perhaps may help you with your, a warm, fuzzy feeling on what we're doing here. Just again, the blower here is extracting gas from the landfill, which you can see in the background here. It is now parked. That gas is, prior to us showing up and installing the biofilter, was directed to the vent. Okay, and that's in red here, going upward. We are now, however, directing that gas via piping that we've installed into the biofilter and gas distribution piping in that filter. The gas then is returned in green to this piping. It's now treated and comes up the vent. We have the ability to control how much gas is either treated and directly vented versus what the amount of gas that goes through the filter. I'll eventually get into this here in a slide or two. We're now flowing most of the gas recovered from the landfill through our biofilter based on the positive performance, which we'll show here in just a minute. Just shows some of the monitoring data. So again, temperature is important, obviously, for biodegradation. We can see an increasing temperature as temperature is increasing throughout the summer. So no surprise. It's interesting to see that all four of these probes are showing us essentially identical temperatures independently of depth and location in the biofilter. It's going to become really interesting to see the extent to which the temperature changes over the winter here in Indiana. And then we see the moisture data on the bottom here. Again, 4 different sensors, different depths and locations in the filter. The general trend is we have an increasing moisture level in the media of the filter. And I think the reason for that is the gas that we're recovering has significant moisture in it. And we have been able to verify that the moisture of the gas leaving the filter is lower than the gas going into the filter. So it's essentially removing some of that moisture. It's also possible that a little bit of that water could be generated through the biodegradation of methane. So getting into the monitoring, there's 3 overall methods that we're using to monitor this particular biofilter, and that includes soil gas monitoring probes installed at different locations and depths in the filter. The right-hand figure shows the locations of those in black. So one right in the middle, and then around more of the periphery of the filter. We installed a small vault here where all of the soil gas monitoring probes terminate, and that simplifies significantly our ability to monitor those probes. And then, to make a long story short, in terms of the soil gas monitoring data, is we have not detected methane in any of these probes since we began operating the biofilter. It has remained less than 500 ppm in all 9 of those probes over all the sampling events. And I should mention that this is a sealed methane biofilter, and that makes it really easy to determine the efficiency at which in the performance of the filter, simply by measuring the methane concentration going into the filter versus the methane concentration leaving the filter. And that data is shown here. This is laboratory analytical data. Samples were collected in the Suma canisters and shipped to a local lab. So on the y-axis here, we have methane concentration in ppm over time for the influent. And we can see that it started quite low, but it is increasing over time, and I'll discuss that in a moment. And we can see that the concentration of methane leaving the filter has remained quite low, resulting in between a 90 to 95% reduction in the methane concentration leaving the filter. It is more challenging to quantify the extent of methane degradation in open methane biofilters, and that's certainly one of the advantages of a sealed filter, such as the one we installed here in South Bend, Indiana. Okay, so transition to our work in just north of or near Edmonton in Alberta, Canada. We've been working with a major oil and gas company here for several years, and I've been very happy that I became associated with the project several years ago. And as a background, we have hundreds of thousands or millions of abandoned oil and gas wells in the US and Canada. It's been estimated that roughly 20% of these wells are leaking fluids, including one or more of methane, brine, and oil. Most of the wells in Canada are located in the province of Alberta, which is where our project is occurring. A little bit of background from our work in Alberta, Canada. There are two types of leaks, as our Canadian folks describe, and that is migrating gas, where gases migrate away from the wells, and then surface casing vent flow, and that's shown in the figure in the upper right here. So in the case of surface casing vent flow, gases accumulate in the surface casing, in some cases even after these wells have been plugged and abandoned. And that is the case for all of the wells that we're working on, or at least 6 of the wells, where they were previously plugged and abandoned, yet still some gas, and it can be quite low quantities, gets into the surface casing. And in Canada, the surface case, the gases accumulating in the surface casing are vented to the atmosphere. And the reason for that is we need to maintain low pressures in the wells, because that has been shown to decrease the potential risk to groundwater. In Canada, if a well is leaking, the rules are that it has to be addressed. One of the issues with that is that many of these wells are located in very remote, heavily wooded areas. So re-abandoning and replugging these wells would come with significant damage to the local environment and ecology, in addition to the high cost, because they're very remotely found in remote areas. And then in addition, the process of re-abandoning these wells and plugging them would come with significant greenhouse gas emissions, which in many cases would exceed the emissions that are originating from the wells themselves, including over long periods of time. We'll just briefly run through the materials and methods and how we're evaluating the flux of methane out of the soils. First of all, we have 2 types of wells, one of which is we have 6 wells, and that's shown in the bottom left figure, that exhibit surface casing vent flow. And in these cases, we are distributing that gas below grade, 2 meters below grade, instead of venting it to the atmosphere. This is showing one case. You can see the excavation in the vent pipe extending into the soils. We have the other 2 wells in our program are cut and cap wells that were found to be leaking below 2 meters below grade. In all cases, these wells were previously plugged and abandoned and subsequently found to be leaking. The approach includes quantifying emissions of methane out of the soils, evaluating the potential effects on vegetation and shallow groundwater. We have, initially observed methane degradation. So a focus of our work has been to understand the natural methane degradation occurring. How effective is it? What are some of the conditions that influence natural methane degradation around these wells, including the changing meteorological conditions throughout the year. We'll get into some of that data. The data on the top figure here shows an example of a vent site. Again, the gas is being vented 2 meters below grade. And what we generally see is if we see emissions of methane, it is highly localized in the immediate vicinity of the vent. And that's shown in the upper left-hand figure. I know you can't see the scale here, but the methane doesn't, in this figure, extends between 1 to 2 meters away from the vent. We generally see, or always see, I should say, indications that at least a portion of that methane is biodegrading, and that includes a depression or lower oxygen concentrations and increasing CO2. which is shown by the brighter orange coloration, in this case, surrounding the vent. In this case, in the upper case, all of the methane was not biodegraded. However, in other cases, all of the methane is degraded, including in this case of a cut and capped well, where we can see, based on a carbon mass balance approach, all of the methane is degraded, and we don't see any evidence of the methane emissions at that particular location. So that is great news. I mentioned that the meteorological conditions do influence distribution of methane in some cases around these wells, and that is shown here. We've been collecting data for, I think, 7 or 8 years now. So we have an enormous data set, which allows us to, obtain a statistically significant data set and understand, to help overcome the variability that we see. So what you're seeing here is the average concentrations of methane in the shallow soil surrounding the vent in different time periods, including February. So that is February over the past 6 years, March over the past 6 or 7 years, and on and on. And what we can see here is that the greatest distribution of methane is observed in March. And that is associated with a decrease in the extent of methane biodegradation, likely because of the cold conditions. And I'm going to show evidence for that next. And that's here. So another way to look at that data is we have on the y-axis, the methane concentration with distance on the x-axis moving away from that vent. In March, we can see that the methane has migrated up to 4 meters away from the vent. However, in warmer periods of the year, we can see less methane migration. And if we look at the CO2, which is a key indicator of methane biodegradation, we see very low concentrations of methane in March, CO2 in March, indicating less extensive methane degradation. So methane biodegradation is a key factor controlling the emissions of methane around these wells, and the meteorological conditions that influence methane degradation play a key role as well on methane emissions and the extent of degradation. As I mentioned, in some cases, all of the methane is degrading. However, in other cases, we do have some wells where some methane is being emitted. And this is an example where we have installed just recently, last week, we finished installing a methane biofilter for a leaking well. And that's shown here. Another slide showing construction of the biofilter. I'll summarize some of our work. We've done a lot of work in Alberta, and this is just a very small subset of our findings, I would say, focused on biodegradation. And that includes that we observe significant natural methane biodegradation around all 8 of the study wells. And in some cases, natural biodegradation in that 2 meters of soil completely precludes methane emissions, whereas in other cases, it does not. And the meteorological conditions, including cold, can influence degradation and the amount of methane that's being emitted. And then, in cases where there is some methane degradation, we have started an initiative to develop sustainable methane biofilters for leaking wells. We've just recently installed our first. And I believe this is, to make this process, our ultimate goal is to develop commercialize the technology. This is not a new idea. Methane biofilters have been around. The concept has been around for a long time. But for I guess many reasons, the technology really hasn't taken off in the industry. So, we will continue to work with our client in Alberta to develop better, more cost-effective and sustainable biofilters. We installed our first last week. We'll continue to monitor that. And our plan at least is to install additional biofilters next year. looks like I'm doing pretty good on time, so we're almost finished here, folks. So I mentioned, in addition to help make the technology has to be sustainable over long periods of time in order for many reasons. We have an enormous number of leaks around the world where methane's being emitted, so it has to be, a fairly easy process. And these leaks are going to continue to emit methane for decades, if not hundreds of years. So it has to be a very simple, sustainable process. But in addition to that, at some point, perhaps there could be regulations that, if the technology does take off, and I certainly hope so, I have a lot of hope for this technology. We need to have low-cost ways to monitor these methane biofilters. And I mentioned how we're doing that in the South Bend, Indiana landfill. We'll also continue that initiative in partnership with our client in Calgary. And I would say we do have some state-of-the-art tools owned by Parsons, including on the left there, a camera-based system to detect methane that has a TDLAS detector, which is quite sensitive, sees very low concentrations of methane. That's great for seeing if there is a leak and identifying where the leaks are, but not so good at quantifying the leaks. And that's really what that second instrument is used there. It's a high flow sampler. It's essentially a vacuum that pulls in the methane, and it has a methane sensor, TDLAS methane sensor. And the combination of the flow rate times the concentration gives you the mass flux or the leak rate of that methane. That combination of tools is currently being used by our folks in Michigan, with the state of Michigan, to quantify methane leak rates for pre-plugging methane leak rates for wells in Michigan. The instrument on the right I pulled that from the internet, but we use the same company, a similar detector, and that company has developed transitioned that particular detector in order for us to monitor methane concentrations coming out of the landfill in Indiana. And we have not yet installed that, but we'll be installing it within a couple of weeks. I see no reason that technology won't work for monitoring methane concentrations in the biofilter. So again, we need low-cost, easy ways to monitor the performance of these biofilters, in addition to developing low-cost, sustainable ways to install them. So I'm going to summarize by sharing just some of the applications for methane biofilters, at least from my vision. Again, we have not invented this technology. It's been around. There's some examples of where it's been applied in the field. But in order to really get this technology to take off, we need to commercialize it. We need lower cost and very sustainable approaches to implement and monitor these filters in a way that assures that methane degradation is sustained over long periods of time, including at landfills. We have installed one so far, and it's been demonstrated to be working thus far very well. Also, we will be installing methane biofilters at passive and active vents, again in South Bend, Indiana. Thanks again to our partners there who continue to support us. In the oil and gas industry, we have demonstrated natural methane degradation, different tools to quantify that process and understand it, and have installed one methane biofilter thus far for a leaking well, and we'll continue that process of developing those and increasing and optimizing those biofilters. And in terms of oil and gas transmission leaks, including tanks and compressors and flares, I see methane biofilters as applicable for all of those scenarios as well, perhaps with the exception of where you have significant leak rates of methane where it's being flared. That would require very significantly sized methane biofilters. So there are some limitations to the way we're currently thinking and installing methane biofilters, but I think there are some ways that we could actually apply these even where there are significant rates of methane being emitted, including in methane associated coal bed methane, including mine shafts and gob gas. And these biofilters would be installed differently, but there's some ideas that we have on how those could be designed, and that is again particularly important in our Appalachian states. Okay, so I am finished with the presentation, and I'm not sure what I should do now. I guess open it up to presentations, or I'll turn it over to Jesse.
Yeah, thank you, Glenn. That was a great presentation. It's great to see such a promising solution to address methane leaks, which has become a big focus in the recent years. If anyone has a question, you can enter into the chat at any time, or you can raise your hand and we will unmute you so you can ask it live. It looks like there are already some questions that are coming in. And for anyone who didn't see in the chat, the link to the PDH form appears to now be working. So if you couldn't access that earlier, it's been posted again in the chat, so you can download that. So our first question, it looks like is, what is the byproduct of anaerobic methane oxidation? Hydrogen sulfide?
Yes.
Yes, so sulfides, yeah.
Well, okay. So that is an excellent question, and it depends on the electron accepting process that is responsible for degrading the methane. If the methane is degrading anaerobically with sulfate as the electron acceptor, yes, you would generate both CO2 and H2S. However, recently methane has been shown to degrade anaerobically under a variety of electron accepting processes, including with nitrate, in which case the end product would be nitrogen gas, potentially with some ammonia as well. And then methane can also degrade. This is really interesting, and I think we see some evidence for this as well at some of our sites, is it can degrade anaerobically with iron in the sediments as an electron acceptor, in which case ferric or oxidized iron, which is oftentimes orange or lightly colored, is converted to ferrous iron, which you can often see visually based on more gray sediments. And interestingly, we saw that when I was out in Alberta last week, some potential indications that we could have some anaerobic degradation of methane. Great question.
Okay, our next question is, do you think these biofilters will degrade over time? And if so, what is the lifespan that you are anticipating?
That is a very, very, very good question. My hope is that we install them and we walk away and they work for decades or longer. And that's been certainly the goal. And so when we create a couple of ways that we help assure that, of course, it's going to be decades. Hopefully, would be decades before we know whether that's true or not. But we include our media is comprised of inorganic materials that will not decompose over time. Generally, we oversize the biofilter, so we're not trying to avoid a lot of microbial growth that could potentially occlude some of the porosity in the biofilters. And then we're including long-lasting sources of nutrition. So the hope is very long periods of time, and only time will tell. But I certainly think, based on Mother Nature, again, we learn a lot from Mother Nature and where methane is naturally biodegraded. There are environments where methane has been biodegrading for eons. And so I definitely think it is possible, simply by simulating Mother Nature, that we have the potential to sustain methane degradation for very long periods of time. That's the goal.
Okay, let's see. The next question we have from Eleanor Larson. Sorry, actually, Aaron Sutton. How do site conditions affect the biofilter design? Do you take into account erosion from heavy rain or snow?
Yes, in fact, just coming back from Canada, we included a slight berm to prevent run-on from running into the biofilter. Other site conditions that we consider include depth to groundwater. So, you in some cases, if depth to groundwater is just a meter or so below grade, then you don't have a lot of room to work with. that could mean that you need to mound the biofilter. Other conditions include the frost line. So in Canada, the frost line can extend down to 6 feet or more, depending on the year and apparently the snowpack. So interestingly, talking with the guys out there last week, if you get some snow, snow is a very good insulator. So there are a lot of conditions that influence the extent to which the soils freeze, but certainly that's a key condition. But we are attempting to mitigate that even in Canada by insulating the biofilters. So those are just some of the site-specific conditions. Another really important one is the rate at which methane is being emitted, which affects not only potentially, it will affect the size of the biofilter that you need, but also potentially the orientation of the filter.
Okay, looks like we've got a live question. Kyle Metz, if you can unmute yourself and ask your question, please go ahead.
Hey, Glenn, great talk. This is, I guess, my question kind of corresponds with Aaron's in the chat, but I can't help but with the orphan well, you have to excavate a whole lot of land to install the biofilter. I was wondering, to keep things cheap and to disturb less land, if you were to engineer the well in such a way so you design, the surface casing pressure leak, and then you just have like a modular sort of above ground, quote unquote, biofilter facility, like in the giant bucket, if you will.
Yeah.
Do you have like a correlation between like surface area of your media and leak rates or anything like that quantified yet?
We know essentially roughly how to size these biofilters based on the degradation rates. But your concept is very good. And it's an example of how, again, we just need to continue to think about how of different options to apply these filters. That is one that we have thought of. And in fact, Jason, I think Jason is on the phone here, who I work with our research and development group. We are planning on developing containerized methane biofilters and applying those next year. So that's a great idea. That's one that we did think of. And I will say that there are many, many other ideas that we have, all, again, just, different options to install biofilters. And I think that's ultimately what we need. Keep our minds open and, continue to optimize how we do this in the most economical way possible. Great idea. I like it a lot.
Just to expand on that, you mentioned Appalachia a few times. I mean, that's where I'm focusing my work. A lot of the orphan wells, when they're plugged, if they're in coal country and they penetrate a coal seam, you have to vent that coal seam to the surface forever. And so this would be a great application for taking care of the natural CBM venting.
I love that idea. I like that one a lot.
Okay, we have a few more questions coming in through the chat. Next question is from Eleanor Larson. What are the costs associated with this technology?
I was hoping nobody would ask that question, mainly because I can't be very accurate in my answer, but I can give you, for example, and Jason, I think Jason is online here, can interject. So the one in South Bend, Indiana, was paid for by Parsons. That is internal research and development money. I think it was roughly $70,000 ballpark to install that. I would consider that a very upper kind of cost because, it has a lot of bells and whistles, some of which we probably don't need. So, coming out of the gates here, we want success stories. But over time, the goal is to reduce those costs. So it just depends on how you apply these biofilters. And of course, depends on how much money you're spending on monitoring them. So again, in South Bend, I do believe here within a few weeks, we have the method to quantify the performance of the biofilter with nobody visiting the site, which will, reduce the long-term operating cost to monitor the filter. So In Canada, I can't even guesstimate right now what that cost is. But again, I think there is going to continue to be here within Parsons and perhaps outside of Parsons work to continue to optimize how we implement this process at a low cost. That's definitely the goal.
Okay, next question we have is from Hao Zhang. What does the biofilter medium typically consist of? Do you need to add any methane biodegradation bacteria to increase the degradation rate?
Yeah, so obviously I'm not gonna disclose everything we know about what we put in the media, but I will say that the medium, the permeability of the media is important. And depending on how you design it, you may increase or decrease that permeability. You could even potentially have layers with different permeability, but you've got to get the gas distributed fairly well through that biofilter media. You need significant contact between the gas and the microorganisms, which could impact how you formulate your media. And then you need long-term sources of nutrition to sustain this microbial approach. And it's all inorganic. So we're not, folks have installed methane biofilters with wood chips. That's all great, but our particular approach is to use inorganic, non-degradable materials where the structure and the porosity of the biofilter will be maintained, because our objective is to walk away from these methane biofilters and let them work for very long periods of time.
Next question is from Krista Stevenson. Does each well require extensive data collection prior to the design and installation of the biofilter?
No, that's a great question. Struggling a little bit to answer it, but no, because really the main thing that we need to know is the leak rate, which is fairly easy to quantify. We do have a lot of data at one well showing that the leak rates are actually, at least at the one well that we monitored continuously, has been fairly uniform over time. So the main thing that we would need is the leak rate. We may or not need the depth to water, although that would be helpful. So yeah, no, we don't need a lot of data collected up front to design the biofilters for these wells.
Next question is a follow-up to that one from Eleanor Jennings. What environmental parameters do you monitor in advance of installation and then during operation of the biofilter? Can you provide examples?
Monitoring parameters. So keys would be leak rate. We need to know how much methane is leaking so that we can size the biofilter. Oxygen can be important. So we need to make sure that adequate oxygen concentrations are either in the recovered gas or the gas stream that we're treating. If not, we need a source of oxygen. We need to understand the permeability of the materials that we're building the biofilters. And in terms of monitoring post after installation, I think some of the keys are moisture, temperature, and gas concentrations, including methane, CO2, and oxygen concentrations going in and out of the filter. So those are kind of the most important parameters. And of course, you could get, as researchy as you would like from there. We are doing some research, more researchy type analyses, including the microorganisms that are degrading the methane. Yeah, so I think nitrogen, phosphorus, nutrient concentrations in the media could be important. But great question, Eleanor.
And it looks like we've got one more question from Aaron Sutton. I'm also curious if you conduct feasibility studies for these biofilters. You mentioned for the leaking wells that costs due to remoteness and greenhouse gas emissions from getting equipment to replug the well were too high. Do you estimate how many pounds of greenhouse gases would be emitted to complete the construction of a biofilter compared to how many pounds of greenhouse gases would be sequestered by the biofilter?
That is an excellent, excellent question. You saw the fairly heavy equipment in the one picture there. And so, yeah, I will definitely do that. That'll be an interesting comparison, but it has not yet been done. But clearly, we have to, we can't be emitting a lot of greenhouse gas in applying these biofilters. So yeah, that's a great point. We'll definitely be diving into those estimates. Again, and independently of what that result is, there are ideas on how to, minimize the use of heavy equipment in constructing these biofilters, and I suspect some of those ideas will be applied very soon.
Okay, it looks like we have one more question from Greg and Dickinson. What is the upper end of the flux rate that your current design can accommodate?
It's unlimited. You can design a biofilter, and build it to any size you wish. So, but there becomes a point in time where the biofilter has to be so big to degrade the methane that it's just not economically viable. So, for example, I had the idea of offshore platforms where there's a lot of unwanted methane associated with drilling the wells offshore. Seen the pictures of just huge flares off of those platforms. That's a scenario where you would need a very large biofilter where it just wouldn't make practical sense to apply a filter for that situation. So, it really comes down to cost. However, I will say there are some thoughts that we have on how we could apply methane biofilters at a really large scale, just in a very different way than we have to this point. So, that's an example is, again, going back to the coal bed methane world, which I have a lot of experience in. It's possible to create methane biofilters in the subsurface, including potentially in the mine shafts. So, again, you just need to keep thinking about how to apply these under different situations, and we'll continue to learn. But great question.
Okay, if anyone else has a question that you didn't get a chance to ask, please feel free to reach out to Glenn directly. His contact information is shown here. As I mentioned before, a link to the form for pH credit has been posted. That link should be working at this point, but if you have any issues getting that, please contact us and we'll get it to you. And if you missed any of the questions during the presentation, the recording of this webinar will be posted on our YouTube channel in the next few days. Glenn, if you can go to the next slide, please. So our next webinar will be on October 9th, presented by Matt Krantz on a success story, soil remediation through horizontal air sparge and SVE wells. It'll be the same time as today's webinar, 12:30 to 1:30 p.m. Eastern. And I'd like to thank everybody for joining us today for today's webinar, and we hope to see you again in October.